it's my pleasure to introduce Sasha Braverman from Perimeter and Toronto, who will speak about Hecke operators for algebraic curves over local non-archimedian fields, a survey of some recent results.
Thank you very much for the invitation. It's a great pleasure to be here. So I've actually given a couple of talks on more or less the same subjects in Cambridge the last couple of years. So I'll try to kind of divide it into two parts. So it will be and so the first part will be some kind of general things, and then in the second part, I would like to concentrate on a particular example of whatever I'm going to talk about in the first part. And this particular example is supposed to have some interesting relation to sort of usual representation theory of p-adic groups. All right, but let me start with the generalities. So let me first so maybe just here. So let me start with first of all with some kind of classical stuff. More or less everybody in this room knows, most probably better than me. So suppose we start, so the classical stuff will go over finite. And suppose that I start with X, which is a smooth projective curve over Q. And well, I start with some G, which is some reductive algebraic. And we consider, well, the standard object can say geometric language is the modular stack of G bundles on X, but I actually don't want to do anything fancy. I don't want to do any kind of real algebraic drawing. I don't want to do geometric languages. I want to really do kind of classical stuff. And so this, I want to actually consider just a set of points of this thing over my FQ, just view it as a set. And then I want to consider functions here. And there are kind of three types of functions I want to consider. So I want to consider, well, first of all, functions will be complex valued for me. And so I can consider what I know by C sub C. This means kind of functions with complex support, but that means functions. So okay, let's just steal a bunch here. There will be all functions, all complex valued functions. All functions, and so these are functions with finite support. And so the most important thing still for me will be this one. And inside this, I'm going to use some kind of mathematical incorrect notation. So I want to say that, well, definitely this sits inside this, but also this intermediate space, which actually is not really intermediate if you do it properly. This is the L2 function, because of course, L2 functions are not really functions, but what I mean by this is I take functions, I take square integrable functions. I mean, things which are actually defined as functions of points.
Well, in this case, they are functions because this is a countable set.
Yeah, okay, right. So, yeah, okay, sorry. Yes, in this case, it's fine. So, I mean, I was jumping out. So, okay, let's just say that, yes. Okay, thank you. The point is that, so what's the story? Well, I mean, these are some versions of the space of homomorphic functions, unramified homomorphic functions. So actually, in this case, the space of all unramified homomorphic forms is this one, and this is just completely supported homomorphic forms, and it's a square integrable homomorphic forms, and this has, all these spaces have an action of a of a very big commutative algebra, and this is the algebra of Hecke apparatus. Now, the Hecke apparatus, so easiest to describe Hecke apparatus have to do with the following. Suppose I take point x and x of a q, but actually later on for me, especially when we move away from a q, it will be very important for me that I can take points over some extensions of this field. So, but let me for a second just take point over the same field. Then I have the algebra, well, no, by AHX, this is algebra of Hecke apparatus. I'll actually say something about it in a second at the point x. So first of all, in algebra, this thing is by Sasha isomorphism. This algebra is isomorphic to complex value. Let's say conjugation invariant complex valued functions on the Lagrange dual group, which is also the same as say complexified Grothendieck ring. Okay, purpose of representation. So the dual group, and so this algebra acts, and well, and so how that and it acts by some particular elements here, act by correspondence. This correspondence is leave on. Let me write here. So, so maybe actually let me remind the easiest example. So suppose that is GLM, and then I can think about bundles as just vector bundles of rank n, and then I consider the following correspondence. I consider two vector bundles E1 and E2 of rank n, and I think about them as locally free sheaves. I consider embedding of E1 into E2 such that E2 mod E1 is a spine forever at x. And so I consider this space, and so this the correspondence from my bond GLM to bond GLM. And so I can use this correspondence to eigen-functions, and fibers of this correspondence, actually each fiber of each arrow here is a projective space of dimension -1. So here, let me say because that will be kind of important in the future, and I can use this as a correspondence, and so this is this correspondence gives the operator which Sasha isomorphism. So this is the Sasha isomorphism, and this is the thing which under Sasha isomorphism corresponds to class of the sort of the logical representation G. So that's all well-known things, and maybe the last thing I want to say about this is right. And so, of course, the standard sort of question when you in sort of Langlands conjecture, which is not a conjecture anymore, in fact, is which is by a theorem by now, is that you want to describe. I mean, the question you ask is how to describe eigenfunctions of these operators and eigenvalues, and so the kind of Langlands correspondence tells you that. By the way, I mean, it's convenient for many purposes to think about this space as kind of some kind of dual to this space. So when you study eigenfunctions, you can ask whether you want to study eigenfunctions here, here, or here. So somehow easiest thing to say is either here or here. Let me ignore L2 for the moment. But basically, roughly speaking, Langlands says that eigenvalues. Well, actually, for this, to be able to formulate this, you really. I want to simply to work over C, but to actually formulate things nicely, you need to replace C by, let's say, QL bar. And so eigenvalues have to do with p-adic G-check local systems. On X, and there's an easy way to. I'm not going to write it, but there's an easy and well-known way how you start with the local system and how you describe the eigenvalues of the Hecke operators. And maybe last thing I want to say is that actually, if I only consider here, of course, I only consider here points which leave over Q, then I only have find many such algebra setting, but I can do better. So we can actually take D, if you take D any divisor in X, which is defined over Q, then we can consider Hecke operators.
The effective divisor, yeah.
Well, yeah, by divisor, I mean actually a set of point. Again, I'm using it. So divisor is not really a combination of points, just a set of points. It's the Hecke operators which kind of leave, which. And so kind of most interesting thing is to consider irreducible divisor. So we consider irreducible divisor, which basically means that it's a Galois orbit of some point. Galois orbit of some x in x defined over FQ bar. Then the corresponding algebra of Hecke operators which leave it as divisor will be actually still it will still be naturally isomorphic to the same thing. So then this H HT, which is the algebra of Hecke operators, which correspond to modifying your bundle set D, is still the same CG. Okay. So this is all very classical stuff. Now, what I want to do, I want to move to the following direction. This is number 2. So now what we want is to replace FQ by F, which is going to be a local non-archimedian field. So you can actually also do it with the Archimedean case, but that has, from my point of view, slightly different flavor. But that will be taught by Pavel Etingof precisely about Archimedean case, and Archimedean case much more is known. But I really want to do the non-Archimedean case. Some initial stuff is similar for any local field, but then somehow it deviates. So okay, so then what do we want to do? So we want to define some space. So we want to consider still the same band G. So now this is
The ask a philosophical question.
Yes.
You're welcome to.
Yeah.
Is there a particular motivation you have in mind to saying, okay, let's replace a field by a different field?
No, not really. It's just you do what you can. No, it looks like. See, okay. Okay, let's try to reformulate the question. So, okay. In 5 minutes, I'll be able to kind of reformulate the question. So I'm going to ask some questions, and I can ask why this question is reasonable. Why do they have sort of? Why do we expect those questions to have a kind of real answer? And the answer to that is I don't know. But so if you ask me whether I'm like 100% convinced that there's some kind of rich new structure there, then I'm actually not. But I hope so. But I'm not like.
But of Archimedean field, it connects all kinds of non-Archimedeans.
Yes, but somehow, but I think that really sort of non-Archimedean cases after you pass some initial stage, it becomes really different. So anyhow, so let me. I mean, there's some things there are very kind of nice and very beautiful and very different from what we're used to, and so at least you can do certain things, and so at least I don't know. Let me present what I can.
Maybe I can more specifically. Do you have in mind thinking that you're working over a surface or something? I mean, I don't know. I'm just
I'd like to do that
on your work. So.
I would like to think that I'm working over a surface, but so far I fail to think that. And in fact, if I get to that, then in this example that I promised. There will be the question. The overall question will be that I can define Hecke operators in this context, and then there will be a question about how to describe the spectrum. And there will be some example where I will describe a spectrum for you, which kind of we'll have to do. I mean, you can relate it to the point of view of kind of living over a surface, but not quite. And so I'll try to get to your questions like very end. So this is okay. So now let's get back to generality. So this is an algebraic stack over F now. What do we want to do? So we want to describe some Hecke operators, but first, I mean, to talk about Hecke operators, we need some space on which they will act. So, let me describe some very general construction of a space. So, okay, so let's do the following thing. Suppose that we have Y, which is an algebraic variety over F. For example, smooth, but actually for now I don't really need to be smooth. Then I can consider a set of points. And then I can consider, well, I want to work with the space which is analog of functions with finite support. So I can consider space of C infinity functions with actual compact support. C infinity just means locally constant. This locally constant functions with compact support. And I'll denote this space actually. Actually, C is not a good note. Okay, look, but I actually want to switch notation. So I'll denote this by S of Y. S for Schwartz. Now I need actually some slight variant of this. So actually, for my purposes, I will need to do it not for functions, but for sections of some line bundles over some powers of the line bundle. So suppose that I have L as a line bundle on Y, then, and let's actually take C to be a complex number, then because I have a homomorphism, so I can consider homomorphism from, have norm homomorphism from F star to R plus, and then I can sort of consider this raising to the power, sort of x goes to x to the power of C. This is C star. So because of this, I can to any line bundle, any complex number, I can associate some kind of C star torus or just sheaf of complex vector spaces on Y of F. So in the result, it's easy to define S of Y sort of L C. So this is kind of compactly supported locally constant fractions of absolute value of L to the power C. So it is that somehow L is an F star torus, so you can apply this map absolute value to the power C and get some sheaf of complex vectors. So this is I mean locally of course this is just the same as taking functions, but somehow globally slightly different, and that will be important for me. Now that's really my thing. What's more important is that we actually need to do this when Y is a stack. So the question is, can we do similar thing when Y is a stack? And the answer is that you can, at least if you have a sufficiently nice stack. And so if you can describe the construction, so suppose that Y is a stack, let me assume that Y can be represented as a quotient of some Z by some G. When this thing is a scheme, let's say I think of finite type, and G is a for my presentation. So I want to assume that, well, okay, I want to assume the following thing that so assume that for simplicity, this is really not necessary, but I'll assume that G is unimodular, for example, GLN. And second is that the map from Z of K to Y of K is surjective. So if you can represent your stack as a quotient by an affine algebraic group, by any affine algebraic group, then you can also present as a quotient by GLN. And if it's quotient by GLN, both of these conditions are automatically satisfied. So that's really you can find at least some such presentation if for any stack which is a quotient by group. And in fact, the stacks I'll describe some construction in this case, but you can generalize it to the case when your stack locally looks like this. And but let me describe what is this. Suppose that again L is a line bundle on Y, and again C is the complex number. Then I can do the following thing. I can consider, I can pull back this line bundle back to Z. Let me call it LZ. I can consider corresponding power of that. I can consider this sections of Z. This and that will be on my group G of F will naturally act. So this is actually my group G of F will add here, and I can take point variance. And I set this to be S of Y, so value of the power C. And then there's a lemma that it's independent. This thing is independent of the presentation. This lemma, well, actually some special case of this lemma, well, essentially this lemma of presentation, this construction, and this lemma is due to Lacebury and Kazhdan, so it's in their paper from 20 years ago. In fact, they have some well, weaker assumptions from the stack, but let me just for simplicity just talk about this case. And then you can generalize this.
What does the absolute value sign mean?
I'm sorry? Sorry?
What do the absolute value signs on L mean?
I kind of try to explain it here. It's what it's just to any algebraic vector bound on a complex number by means of such a homomorphism, we can assign sheaf of complex vector spaces.
Line.
Line, yes, I said L is a line.
So you take absolute value of the transition function.
Well, I mean, you just have an F star torso from this. This way, you get a C star torso, and then given a C star torso, you can construct this sort of sheaf of one-dimensional C vector spaces. Well, sheaf with Stokes are one-dimensional C vector spaces. There's an easy generalization of this can generalize to the case when Y is locally Z mod G. So by taking just some kind of direct limit, so in particular, we can do it for Y being equal to this 1 G of X. And I also want L, and I'll explain in a second what I need L for. So the L I want to take the canonical bundle 1G, which is some kind of determinant bundle. And for a second, I want to take arbitrary C, but actually very soon I want to take some specific C. And so you can define some space level called S sub C of 1G. This is just this S of 1G. This corner. Now, okay, so this is at least a vector space. So now, what can we do with Hecke operators? Now, for generic C, you don't have Hecke operators, but the claim, and so this claim is it's actually hidden in my old paper with Kazhdan, but in this kind of particular form, it was formulated in a paper by Etingof and Polishchuk. Is that if you take C to be 1/2, and you call this C critical, so this is kind of critical level, and then you have an algebra of Hecke operator. You have a lot of Hecke operators acting. So I'll comment on what it means more precisely in a second. So then you have Hecke operators. So let me say a little bit more precisely what it means. So let me first say, although later on that will be not enough for me, but let me first say when I take a point of my curve defined of my field, then I consider Hecke, then I claim that for every lambda, which is dominant weight of G. We can define some h lambda, which actually is, well, multiplied by G from S1/2 to S1/2. And they all h lambda x, let's say, and they all commute. And actually, definition will be such that something much simpler than in the usual case will happen. They will have the property that if we consider hx lambda and hx mu with the same x, that will be just the same as hx lambda plus mu. I'll comment later about what we actually don't understand well what this Hecke, what kind of algebra in the philosophical sense this Hecke to form, but just the definition is the following. Definition is that we consider, and so I'll try to explain where this 1/2 is coming from. The definition is that we consider the following stack. So for every lambda, we consider the following things. We consider pairs, let's say E1 and E2, these are G bundles. Then some kind of kappa, which is an isomorphism between those away from my point X. So this is the kind of Hecke step at X, and then kind of it's known that in general we can naturally decompose this Hecke stack into locally closed substacks which correspond to lambdas. So for every it kind of says that we consider this. So for every lambda, it makes sense to say that we consider such an isomorphism which sort of has pole for the lambda at X. So for every lambda, we have. So this corresponds to kind of the decomposition of the fine grass margin of G. So we have locally closed substack. Yeah. It's lambda. And this substack, it's a correspondence between Bungie and Bungie. And the point is that, so what do we want to do? If I have a correspondence, I want to take something here, I want to pull it back, and I want to push it forward. But now we leave our local field. Our local field, what is, well, pulling, for example, let's do it for functions. So if I take a function, we pull it back, what does it mean to pull a function back? That's easy. But what does it mean to push a function forward? Well, pushing something forward means that you want to integrate over the fibers. And to integrate, you can't integrate functions, for example. You only can integrate measures. And this is where this 1/2 becomes critical, pun intended. So the idea is that there's the following lemma that if you take well, okay, so there's the stuff about that our space is defined as a space of covariance and so on. Let me kind of ignore this for the moment, but basically the statement is that you can make sense of this. And there is this kind of that if you, well, let's call this map alpha and beta, for example, that if you take some phi, which is an S1/2 and 1G, then if you pull it back, then the point is that this becomes a section of the canonical bundle along the fibers. I'll say it's a measure on the fibers of beta. I mean, it's actually an algebraic statement. So the algebraic statement says that if you take, and it's true for any lambda. So if you take the square root of the canonical bundle on Bungie, pull it back on this map and restrict it to every fiber, then every fiber is isomorphic to the canonical bundle of the fiber. For example, I talked about this case when about this correspondence, which had to do with the standard representation of GLN, and there all the fibers were projective spaces, and so there's no natural measurement projective on projective space, but somehow but here it's for this critical level, we don't have this problem. And so, it's this thing is, if I pull back this critical bundle under this map and restrict to fibers, it's isomorphic, it's almost canonically isomorphic to canonical bundle of the fiber. So almost means that it will be canonically isomorphic if I choose a trivialization of the canonical bundle of X at this point. And I can actually, it's easy to say how much it depends on that, but let me tie this up to the right. So essentially, this pullback of this square root of omega here is isomorphic to canonical bundle. So that's kind of luck. I mean, it didn't have to be so.
But don't you have to choose a spin structure in general if you group?
No, but I'm doing the point. I'm fixing points. I don't need to. So if you want to study dependence on this thing on X, then somehow what you're saying somehow becomes important. But I don't want to do it right now. Okay, so now just a remark is that we can do, as in the case of finite field, we can do more, and now it really becomes much more. So we can also do we can define these Hecke operators which leave an arbitrary divisor.
Did you say anything, or will you say anything about they all commute comment?
Well, for a particular X, they definitely commute. Kind of follows from here. See, this is different from.
Or will you say something about that equals?
Yeah, actually, maybe I'll say something else. So I said that somehow. There's a kind of slightly non-trivial thing which kind of has to do with some algebraic geometries that here in general, unlike in this case, so in the case of the standard operator for GLN, the fibers are actually compact, so I don't have convergence issues. So in general, the fibers are not compact, so the fibers of this map are, I mean, algebraically, there's some kind of algebraic varieties which are not projective, but the integral turns out to be still convergent. So it's just a fact. I mean, and it's kind of algebraic fact, so you don't need to do any analysis for that. But true, I mean, they can, so this hx lambda commute.
I mean, the variety is not compact, but when you are integrating, you're going to have compact support. Right?
No, absolutely no.
But will be convergent in the sense of geometric progressions.
Well, I mean, okay, it will be convergent. First of all, it will be absolutely convergent, but there will be some algebraic reason for that. So they commute, and more generally, you can take X to be in X of E, where E over F is some finite, let's say, Gauss, let's define a Gauss extension. And then actually, well, we can start with this thing, but actually our modification will be done along the corresponding divisor, and the divisor will be the Galois orbit of X. So modifications that devise E, which is the Galois orbit. So this way, I mean, because now we have like our local field has like a lot of extensions, so doing this is really important. So in the sense that somehow we get much more than just considering points over which are defined over F, and all these guys, all these things can be. So now the basic question is question to which at the moment I don't have the answer, but I'll try to say some things about it. How to describe eigenfunctions and eigenvalues. We have a space. The space has an action of a huge commutative algebra, and so we can. And so when I say eigenfunctions, we can do two things. We can study eigenfunctions in that space, or as in the case of finite field, we can also study eigenfunctionals. We can study eigenvectors in the dual space. That will definitely give us much more. But actually, it's so we can study more, right, like eigenfunctions. just let me make a remark that if you go back to the case of finite field for a second, then and that will be maybe useful for something I'm going to say in a few minutes. If we consider this, so we have this. So okay, now back to. So consider this as a bunch of u. So it sits inside all functions of bunch of u. And so eigen-functions of Hecke operators here in the subspace are, well, not really by definition, but by some by an easy result, are called hospital eigenfunctions. I guess for this to be exactly right, I need to assume G is semi-simple, not reductive. So yeah, so eigenfunctions. Otherwise, you won't have those functions. Let's say it's semi-simple. And you know, and also if you think in terms of L2, then one sort of, I mean, eigenfunctions for GP here, they have to do with discrete spectrum in L2, and usually in L2 you have a little bit more of discrete spectrum, but most of the discrete spectrum comes from here, and most of the rest is continuous. Okay, so in some sense, if we're studying really eigenfunctions inside our space S, this should be thought of as studying analogs of classical eigenfunction. But let me also make a remark is that before I form on some theorems, let me say that we can also do a variant. Well, actually, in the case of finite field, we could have done a variant, but also here we can do a variant, and the variant is that that you can also consider, in addition to considering modulus bundles on a curve, we can consider if we can fix some other divisor, divisor t, divisor, and so we can consider bundles with some structures, some kind of level structure, some realization, so maybe tracing some infinitesimal neighborhoods at D with some structures at D, and then Hecke operators at X, which does not belong to D, still X. And so we can study and we can do everything I said in that context as well. The reason I'm saying this is that the example I promised to discuss in the end is actually of that kind. So I mean, the kind that will take projective curve and some particular additional structures, projective lines, sorry, with some additional structures. So just you can't really act by Hecke operators at the points of D, but at all other points you can. So. Okay, now let me form some general theorems, and then I'll concentrate on examples. So first of all, you know, our definition of space is very, very abstract. But so questions, can we get some kind of boldness, and also can you produce some examples of eigenfunctions? Now let me form the theorem, or so this. Okay, let me put this theorem in quotation marks. What it actually means is that this is an actual theorem for SL2, and so actual theorem for SL2, and same method should work for in general, but we're just lazy to do this, and this is due to myself, T.Kazhdan and Polishchuk.
The theorem or the laziness?
Laziness is always due to me, you know. It's just so You can say that the theorem part is due to my co-authors and the quotation marks are due to me. That's it.
Which means that they thought it was a theorem and you discovered that it was not quite.
No, it's okay. Anyhow, so this is just something. Anyhow, so the result should definitely be true always, and it's kind of clear what the argument should be, but we're just lazy to do that outside of SL2. Theorem says the following, that let's take for simplicity genus, let's assume the genus of my curve is greater or equal than 2. So here I can see the curve without any additional structures to any points. Then this S 1/2 of 1G embeds into the following thing. Embeds into C infinity function. So again, C infinity in this context means just locally constant. 1G very stable of S. And so I'll comment on this notion in a moment. So well, and actually and they also lie and also all the functions lie in L2. So also, well, let me write it down. I'll make some point about it. C infinity is sort of also kind of 1/2, so it means that we can see the sections of the corresponding line bundles here. So L2 the same. So let me make some comment about this. So first of all, this let me assume for simplicity that G is semi-simple, or even let me assume G is adjoint, just to assume G is adjoint. Then you have actually the space of stable bundles, substack, open substack of stable bundles for genus of these two. This is a scheme. This is open and dense in the full stack. Now, there's also some notion which I, because of lack of time, prefer not to define, but there's some still open and dense subset of very stable bundles. For those who know those words, very stable means that any for such a bundle is very stable by definition if every nilpotent Higgs field at this bundle is 0. That there are no non-zero nilpotent Higgs fields. And so there's a theorem that not completely logical theorem that every very stable bundle is stable. So that's a smooth variety inside our bundles, and the claim is that we can actually naturally so we have this absolutely defined space, which somehow we had to treat the presentation, take some covariance, prove a lemma that it didn't depend on the presentation, and so we actually had to do this locally. So that's some like combination of crazy procedures. So in the end, all these things you can naturally define them as some kind of locally constant functions with a set of stable, very stable bundles. Funnily enough, they're not locally constant on all stable bundles. Well, no, there's a conjecture that in all stable bundles they are continuous, and this is for SL2. This is equivalent to some very crazy conjecture in algebraic geometry, something about some theta devices and so on. But anyhow, so here they're just locally constant, and in addition, and that's actually much less trivial, they're also square integral. And by square integral, let me make a comment about this. So in general, if you take any variety, if you take functions on a variety, then there's no notion of L2 functions, because again, to define L2 product, you need a measure. But here we're doing half measures. We're doing square root of the canonical bundle. And so, so actually on any variety, there is some L2 space. It just consists not of functions, but it consists of sections of the square root of the canonical bundle, which are square integral. And so all of these guys, they turn out to be functions, well, not functions, but sections of this line bundle, but kind of like functions, not with complex support anymore. So on this open subset, then they don't have complex support, but they're square integral. Just a fact.
What is the idea of the proof that they're square integral?
I don't have time. I can explain to you. So now so I promised to produce some eigenfunctions. Now let me do the following thing. Let me describe some general procedure, and then I'll apply it to functions. Suppose that y is any step. Let's say smooth. Y is smooth step, and I take this L to be canonical bundle of y, then I can do the following thing. I claim that there's a map from, if I take this as what I call S of a smooth stack, let's say, suppose everything is smooth stack over O, which is the ring of integers. So then I can also then reduce it, and so then all maps to FQ. This is the residue field, and I can consider S of y of FQ, and there's a natural operator which I, for reasons that I don't have time to explain, I call it Eisenstein operator. It's kind of like Eisenstein series, but in the case of Bungie, but I won't have time to explain why. There's an operator two sections to this SC of y. Well, SC of y means that I can see this C power of this guy for every C.
So maybe I missed, what was the O?
Always the ring of integers in F. So I'm doing everything over local. I have a non-archimedian, local non-archimedian field. It has a ring of integers. So I assume that my stack is not just a stack over F, but it's defined as a smooth stack over O. And then the point is that I can I have the following correspondence. So I have this y of FQ. So let me kind of explain what happens in the case when y is a variety. But then the claim is that for stacks I can do the same. So I can consider this y of f here. Here I can consider y of O. And I have natural maps here and here. So this basically this thing is is given by this Eisenstein operator is given by this correspondence. But the point is that where does C come from? C comes from the following fact that if I consider this. So if I consider, okay, let me call this maybe in Q. Well, Q is not good. Pi 1, pi 2. So if I consider the pullback of absolute value of omega y on this map, then this trivializes. It's just the fact that, for example, if you have a smooth variety over integers, then it has a set of points where integers has a canonical measure for smooth varieties. That's kind of what's being said, essentially. So
C critical here?
no, C here is anything. Because this thing trivializes, I can actually view. I can do this for any C. And in fact, this theorem, I can. This L2 part only makes sense for the critical level. This thing makes sense actually for any level. It actually will not be true on any level. It will be true for generic level, but generic includes critical. So I can actually write down explicitly which levels are bad. But and so this is again theorem 2. So says that again it's theorem in quotation marks in the same sense as before. Namely, it's an actual theorem for SL2. I mean, the proof is kind of written down, but and similar proof should work in general, but we didn't do it. Is that so? Now we apply to C equal to 1/2 and y equal to Bungie, and then we get an operator from. So again, this is an operator from S of Bungie of FQ. Yes, for this I have to assume that my X is defined and smooth. That's an additional structure. So I can write this operator which goes from here to X is y. X is a curve. I'm doing nothing for a curve. Just to play this game, I need the curve to be defined not over the field but over the integers, and it has to be a smooth model over the integers.
Oh, I see.
So then there's this operator, and this operator, first of all, it's okay. So this is S, and here is 1/2, and so the first statement is this operator is unitary on constable functions. Unitary, in particular, injective on constable functions. But it's not injective on all functions. So in fact, if you consider Eisenstein part, then for SL2, it will typically have like, on the Eisenstein part, it will typically have like rank 1. So it kills more or less almost all non-cuspidal part. But the cuspidal part is injective. And also this thing, okay, so this I have to, it sort of commutes with Hecke operators in the appropriate sense. So let me comment on this appropriate sense. I'm running out of time. So I wanted to really talk about example, but let me just say that, okay, let me for simplicity do it in the case when I start at the point my curve defined over path, not over the extensions, then the claim is that there's a canonical homomorphism, which actually it's actually an isomorphism. So there's some algebraic Hecke operators actually at this point, and there's a homomorphism which is actually an isomorphism. In this, the corresponding also, if I because my curve is projective, x of f is the same as x of O. So and then I can reduce everything modulo maximal ideal. So if I start with a point here, I get the point x bar, which is here. So it's algebras Hecke is now usual spherical Hecke algebras of the form of Q, leaving at the point x bar. This thing is a is an isomorphism. I can geometrically define it. Now here I have this operator, this h lambda. You can ask where do they go here, and the answer is I don't know. I actually do know. See, because these guys are kind of multiply nicely. For example, it's enough to define them. For example, fundamental weights for GLN. It's easy to do because maybe I'd make a comment here that this. Well, maybe I shouldn't make. Well, anyhow, so for GLN, it's easy to define the fundamental guys. Just go to the corresponding fundamental guys here. For arbitrary groups, I don't know. I computed, for example, the answer for the adjoint representation for arbitrary group, and that's I can't really make sort of categorical sense out of it. And situation is even more complicated. It's we can also do same for x in this S of p that I described. So here the interesting case when E is a ramified, is a purely ramified extension. Then here I get the divisor out of this, I get the Galois orbit. But when I reduce, if it's a ramified extension, all this Galois orbit becomes 1 point. So I actually get a homomorphism from from the corresponding Hecke algebra leaving this divisor to the Hecke algebra over finite field leaving at 1 point. And again, sort of you can ask where this h lambda goes, and that already for GLN, I don't know the answer. Actually, for GL2, I don't know the answer. I made some computation with this for quadratic extensions, for example. There's some nice formulas, but I cannot kind of make a system out of this.
But if your point is over f, then for minuscule representation.
Yes. If the point is over f, then for minuscule representations, then you're fine. But if the point is not over f, then for minuscule representation, it's not clear what happens. And so, but
if you know,
but the point is that I can define this homomorphism. Let me call it eta x. And so the claim is that this Eisenstein operator commutes with this thing. So in other words, if I take Eisenstein of some phi and apply some Hecke operator at x space, then that's the same as to consider Eisenstein of this eta x like to hx to phi. And what this implies is that if phi if it was a Hecke eigenfunction of a finite field, then Eisenstein of phi is now a Hecke eigenfunction. But the funny thing is that because of the problem I talked about here, I don't know what eigenvalues are. I know it's an eigenfunction, so for every cuspidal, so yes, and in particular also from here it follows that to every cuspidal eigenfunction of a finite field, I can construct a non-zero eigenfunction over local field because the Eisenstein operator on cuspidal part is injected. So the upshot is that now, for example, I mean, it's definitely not, everything is like very small portion of eigenfunctions I have here, but at least every cuspidal eigenfunction of a finite field, which is a kind of very familiar object, I can construct a Hecke eigenfunction in this world. The problem is, and that's kind of part of the problem why we can't formulate any analog of Langlands conjectures here, is that I don't have any language now to describe the eigenvalues. I know that's an eigenfunction of a very particular Hecke operator, but I can't write a formula for the eigenvalues. I mean, in this particular case, writing formula for the eigenvalues is equivalent to describing this homomorphism.
Sasha,
Yes.
is this Hecke algebra you have, is this supposed to be a subalgebra of some much bigger, like double affine type object, or is it that modifying also in the local field?
Okay, I
directly?
have about 5 minutes, so it's I think double affine appear in some very particular example. That's the example I want to talk about right now. So, but in general, I don't think it has anything to do with double affine algebras with this. Maybe it does. Anyhow, so that's kind of the general story. I mean, I know some other general facts here, but I don't have time. So let me switch to very briefly discussing an example, unless people have questions. Okay, let's consider the following example. Let's now consider the curve for P1, and I will consider bundles with trivialization at 2 points. So I consider bound G at P1, and I write 0 infinity. That means trivialization at 0.
When you say trivialization, you mean parabolic structure?
No, I mean actual trivialization. An easy exercise, first this thing is stratified by isomorphism classes of bundles on P1. And the best best isomorphism class of a bundle on P1 is the trivial bundle. Now for trivial bundle, trivial bundle in this case is an open condition. So it gives some open thing in this substack. And so if I can say loss trivialization, just says that it's just the group G itself. So the stack is a kind of static compactification of the group G. Now, by construction, actually for any C, I get a map now from SC of G to this SC of this stack. Well, and actually on G, the canonical bounds trivialize, so I can just I can erase it here, so I get just S for G to, this is just for any open embedding, I get such a map. Now, in general, if I have just an open embedding stack, because I have this covariance construction, it's not always injected. It's very easy to give examples when this map is not injected, but here it's actually injective. It has to do with the fact that all the stabilizers, this thing is a stack, but all automorphism groups in this case are unipotent. Because of this map is, so in this case, this map turns out to be injected. Also, the group G times G acts on everything. So G of F times G of F acts, so everything is a representation of this group. So this big thing, it actually contains the regular representation of G inside. Now, lemma, which is very easy, I won't explain the proof, is that this map becomes an isomorphism, let me call it I. This map is an isomorphism in the cuspidal part. I is an I. So in other words, if I take the quotient, if I take the co-kernel, then everything in the co-kernel is not cuspidal.
Did you say what is the map? Is it something that's zero?
Map is, it's just, it's a very general thing. Whenever I have a stack and an open subset, I have a substack, I have such a map. So let's consider varieties. Okay, we consider functions with locally constant functions with complex support. We consider locally constant functions with complex support and an open subset.
Great.
So the claim is that in this, for stacks, it also makes sense, except that for stacks in general, this map, it's always defined as a map, but it might not be injected. But in this case, the stack is sufficiently nice so that it is injected. So it's an isomorphism on the cuspidal part. But now it becomes very funny for the following reason. Because on the other hand, this thing has an action of Hecke operators, which live at all points away from 0 to infinity. And that's some structure which, on the cuspidal part, we just get the cuspidal part, absolutely classical object, cuspidal part of the regular representation of our p-adic group. But suddenly we have a huge commutative algebra acting on that. It's supposed to be some kind of classical object, but I don't know how to describe it in classical terms. So question, what are Hecke operators on this past D.Kazhdan. And well, it's been 2 minutes, so I think I started a few minutes late. So I know one example. Let me describe this one example.
And what happens if you have 1 point instead of 2 points?
Well, just take point variance with respect to one coefficient. Well, in this case, I mean,
Also,
from this point of view, you get nothing interesting. So, I mean, the classical part disappears. So, so you know, this part just becomes, this part just becomes a point. So this thing becomes just one-dimensional space. So, so example is the following. Let's take group to be GLN. I'm going to get better to PGLN. Let's be G to be PGLN. Then it's I want to consider kind of fundamental Hecke operator. But actually, if I put the fundamental Hecke operator at 1 point, it's very easy to see that I'll get just 0 on the classical part. So the kind of first non-trivial thing I can do is the following. Let's consider E over F, an extension of degree n. And let's consider X to be the point in E star. And let's consider H as this is kind of fundamental, I mean, the one corresponding kind of to the first fundamental weight, fundamental Hecke operator at X.
But E is not required to be a field, yes? It's a,
No, it's a field.
you cannot take F plus F plus F.
I'll get 0. So I really want it to be an actual field. So then the point is that E star can be thought of as a torus, as a maximal torus inside GLM F, and I can further project it to GLM. So this is kind of canonical after conjugacy. So if I take my point X, it defines me canonically conjugacy class in this group. So right, and so my Hecke operator, the point is that maybe there's one thing I forgot to say. So I want to think about it in the following way. So I mean, classical representation is kind of discrete. So I can decompose this. So if pi is an irreducible classical representation of GLPS, and H is some Hecke operator, then I can consider corresponding kind of pi as a typical part of the regular representation, and on that thing, this Hecke operator will have to act by scalar. So in other words, I can make sense of the scalar h of pi. So given my Hecke operator and an irreducible classical representation, I get a complex number. And the actual question is, what is this complex number? So we know that Hecke operators correspond to just choosing some divisors and some co-weights. Irreducible classical representations, for example, we have the Langlands conjecture, which again in this case is known. It's actually have to do with the representation of the Gala group and the dual group. So what are these numbers? In general, I have no idea. So here's the only example I know. So then the claim is that in this case, this h of pi is just the character of pi computing at the point x. Just a simple computation. So these numbers, they're kind of generalized characters to some extent, but I don't know what they are. For example, I don't know how to describe them in terms of Langlands conjectures and so on. So, but I get this kind of absolutely for free. So just by kind of doing nothing. I'm sorry.
So the only elliptic character.
Yes, only elliptic. Yes. But I have to say that this operator is a kind of non-trivial in the following sense. I can't really write them down by an integral, because somehow this procedure involves this point variance, and it involves this thing that somehow I have know that this on the classical part, this I mean the principal Hecke operators act on this much bigger space, and in order for them to act on the classical part of the regular representation, I need to know that this isomorphism, that this map is an isomorphism of the classical part. But this thing is kind of very non-effective. In other words, I'm saying that if I know that I have some classical guy here, I can kind of rewrite it as coming from this open subset, but I can't really do it effectively. So therefore, I don't have any way to write these numbers by an actual correspondence or something. But the definition is absolutely rigorous and very simple. So I have these numbers just for out of nothing. And so that's the only example I know how to compute them. And I'll probably have to stop. Maybe last word I say is that the thing that I was going to talk about, it had to do with David's question, is that if in addition, you can consider the thing part here, which is kind of opposite to hospital. Namely, you can consider, let me speak just 1 minute. Say so kind of opposite extreme is that I consider this as 1/2 of 1g1 to infinity, and now I can consider the part which is invariant under the over times over 4. And this thing turns out to be by actually a result of Kapranov essentially. This thing has two commuting action of the double affine Hecke algebra at the critical level. So this actually for any C has an action of, I don't know how you're supposed to denote Daha. So this is some HC times HC, where, well, this is some non-standard parameterization with parameters having to do with Daha. So the idea is that critical level corresponds to the situation where it's almost commutative. And so for C equal to 1/2, it has a big center, and this H 1/2 has huge center, and which is known to be isomorphic to coordinate ring of some kind of collinear modular space.
Multiplicative collision.
Yes, or relativistic collinear modular space. And Hecke operators become so one result, this is actually joint work in progress with myself, with D.Kazhdan and Sasha and Etingof, is that this thing is essentially a regular bimodule. Kind of means that it's free of rank 1 over every copy of every one of those copies, and so
But twisted like something like.
but I'm running out of time, so I don't want to talk about it. And so from this it follows that this kind of full algebra, full Hecke operators we have here, it will map into functions on the collinear modular space. And in fact, in this case, if we consider this Iwahori part, then the spectrum of the Hecke operators is this collinear modular space. And the problem is because we don't have any modular interpretation of collinear modular space, that's another thing which kind of prevents me from formulating, from kind of understanding what the angle of language conjectures in this world would be, because we don't have this collinear modular space doesn't really have any kind of reasonable definition. So that's why I'm kind of stuck in terms of formulating a general statement, but I think that something is definitely going on here. And okay, I have to stop, sorry for going.